for coming to this presentation about Omid. My name is Daniel. I'm a research engineer at Yahoo at the Barcelona office. I'm the main Omid developer, and also I'm involved in other Apache projects such as S4, and also I contributed to other projects like Zookeeper and HBase. So let me start by giving an outline of this presentation. First, I'll talk about what motivated us to start this project. Then about the main goal of this project, which is having transactions on HBase. Afterwards, I talk about the architecture of the system, the design decisions we took, and why we took them. I'll present some examples of how the system works and about use cases as well. Finally, I'll finish talking about the current challenges we face with the project and what we are doing about them to improve this work. So, as you might know, traditional databases have a very nice set of features such as SQL support and transaction support, but they lack scalability. And that's where the community started the NoSQL movement to improve the scalability of these data stores, but sacrificing the support for SQL and transactions. We found that there are some use cases that require both scalability and maybe some consistency guarantees that NoSQL databases cannot provide. And we thought that we could bridge this gap between the traditional databases systems and the NoSQL data stores. There are other factors that also motivated us to start this project. For example, transaction support in HBase is a common request. There has been many requests like this in the mailing lists. Also, Google implemented transactions on Bigtable on their Percolator project. So we know that it's actually possible to have transactions on NoSQL data stores. And Google introduced this concept of incremental processing on the same paper, on the same Percolator paper, which allowed them to reduce the MapReduce latencies from several hours to just a couple of seconds or minutes using this paradigm. So for those not familiar with the incremental processing paradigm, in the left we have the traditional MapReduce paradigm where we have an initial state, and then we run a MapReduce job to generate a completely new state that completely overrides the previous state. On the incremental processing paradigm, which is an online paradigm, we have a shared state, and we have many small updates, incremental updates to this shared state. And we achieve with this very low latency from the content ingestion until we make this content available on the data store. And for this, we need transactions since we have concurrent updates to this shared state. For example, Google reduced the crawl to index time dramatically since from hours or even days to just a couple of minutes. So we decided to give it a shot and implement transactions on HBase, and we achieved this with this project, which is called Omid. Omid means hope in Persian, and we chose that name because Omid is an optimistic concurrency control system. So this means that it's a lock-free system. So clients don't hold locks on the database to modify it. This means that there are no liveness issues. Clients always make progress regardless of what other clients are doing. We implement Snapshot Isolation on this project. I'll explain later what this is. And the main goal was to have a very low overhead compared to bare HBase. So we wanted to achieve the same throughput without transactions and with transactions enabled. And as we see, we achieved that. This is an open source project. Please visit the project webpage, download it, try it, and if you have any questions, please ask. So as I said, we implement snapshot isolation, which you might be familiar with, but basically this means that all transactions read from a snapshot of the database. And a snapshot is an immutable set of an immutable snapshot of the database, so it cannot be modified after it's been created, and it basically contains all the values that have been committed before the transaction started. To guarantee snapshot isolation, we have to abort some transactions if two conditions apply. If transactions overlap in time and if they write to the same row, they are in conflict, that we have to abort one of them. So here we exemplify these cases. We have several transactions, A, B, C, and D. We see how the transactions behave in time. So for example, the first transaction to start is the transaction A. And we see how they overlap in time and the write set of each transaction. So to guarantee snapshot isolation, we have to check whether transactions conflict between them. So we see, for example, that transaction B is overlapping with transactions A and C, but since transactions B and A don't write to the same row, there's no conflict between them. On the other hand, transactions B and C are overlapping and they write to the same row, so we have to abort one of them to guarantee snapshot isolation. As I said, this is what Omid implements. The model is based on. So the architecture of the system is very, very simple. So we have a centralized server called the status oracle. This server holds all the transactional metadata and is responsible for handling the conflict detection and aborting transactions to guarantee snapshot isolation. We have the transactional clients, and there's a surprising feature of this system, that is that we replicate the transactional metadata that the status oracle holds onto the clients. And I'll explain why we do this in a few moments. And then, lately, we have the HBase system that the clients write directly to HBase. They don't go through the status oracle. So this allows us to achieve the same throughput that HBase provides without transaction support. The status oracle maintains the transactional metadata, and it maintains it in memory. So obviously, the memory of the machine is limited, so we have some kind of garbage collection mechanism. And we have to evict some transactional metadata. But we have to take into account that we have to maintain the consistency guarantees. So for this, we keep what we call the low watermark, which is basically the oldest known timestamp for the status oracle. And what we do is to abort transactions that are older than this low watermark. This is the transactional metadata kept at the status oracle. So transactions are identified by their creation time as the snapshots themselves. But for guaranteeing snapshot isolation, we need the commit timestamp of the transactions. And we keep a mapping between the start timestamp and the commit timestamp at the status oracle. And this is the blue table on this figure. We also need to guarantee snapshot isolation, and for that we have to abort transactions that write to the same row. And we keep some metadata on the green table about what was the last transaction that wrote to a given row. And this is actually the biggest memory consumer on the status oracle, because we need an entry per modified row on the whole system, on the whole data store, and there could be thousands of modified rows per second on the whole cluster. We also keep other metadata such as the low watermark and the list of aborted transactions and so on. Then, as I explained before, we replicate the metadata from the status oracle to the clients, but the trick is that we don't replicate the whole state of the status oracle. We just focus on some specific parts of this metadata. We do this to minimize the overhead and to avoid that the status oracle becomes the bottleneck of the system. We want the clients to communicate directly with HBase, and we don't want them to go through the status oracle. So, as I said, clients guarantee snapshot isolation on their own because they have all the metadata that they need to guarantee snapshot isolation. They ignore data that is not on their snapshot. They write directly to HBase, for example, and the status oracle is only responsible for resolving the conflicts. This operation, the metadata replication, is expensive, but is scalable up to 1,000 clients. And there are simple tricks to go beyond that number of clients. For example, having gateways to the system, such as HBase does with thrift servers, for example. So let me do a small recapitulation of the architecture before explaining how the metadata replication works. So we have the same figure as before, where we have the status oracle, the clients, and HBase. Now I'm showing the metadata on the status oracle. And on the next slide, I show what part of the metadata we replicate to the clients. So as you see, we don't replicate the green table, which, as I explained, was the main memory consumer on the system. So with this, we avoid the bandwidth consumption and the memory consumption of the clients. And also, we show how we in HBase we don't keep any metadata apart from the start timestamp of the transactions that grow each value. Let me compare this design with the one that Google followed in Percolator. The main differences are that we are log-free, and Percolator does have logs on Bigtable. And this is very important because if a client crashes while holding a log, it could stall the rest of the clients that try to access the same data. We also maintain the transactional metadata in the status oracle and replicate it to the clients, but Percolator maintains it on Bigtable as well. We think our design is better, obviously, because we achieve the raw performance of HBase because all the transactional operations are off-band. They don't go through HBase. So in Bigtable, for holding logs or committing transactions and so on, you need to perform extra operations on Bigtable. Whereas on our system, these operations happen through the status oracle, which, as I show, is not the bottleneck of the system. So we can achieve the maximum throughput of your HBase cluster. So this seems very complicated, but actually the API we expose to the user is very simple. We have a transaction manager which is in charge of starting transactions, committing them, and so on. So when the user starts a transaction, it receives a transactional context. And then we have a T-table, which stands for transactional table. And it has the same API as a normal HBase API, but each method receives this transactional context, and you can attach these operations to a given transaction. I'll explain how this works in practice, both the API and the system, side by side. So suppose that we have a running system with some data stored in HBase, and we have some client that is going to start some transactions and perform some operations on HBase. So at first, it has to start a transaction, and for this, it contacts the status oracle, which returns a fresh transaction with start timestamp 25, for example. The client wants to get data from HBase, but in a transactional manner, of course. So it uses the transactional API we provide, and wants to read the row R1, for example. As we explained before, the data in HBase is tagged with the start timestamp of the transaction, but we need the commit timestamp to guarantee snapshot isolation. Luckily, we have this metadata on the client. We have the blue box on the client, and we can map the timestamp of the value, which is 10, to the commit timestamp of the transaction, which is 20. So we can guarantee the snapshot isolation at the client level without contacting the status oracle. All the data operations that to HBase aren't through the status oracle. Suppose that the client wants to insert some data. For example, it wants to override this value with another one. So it simply writes to HBase with the start timestamp of the transaction and the new value. Since HBase is a multi-version database, it keeps the old value around. So if a concurrent transaction wants to read it, it will read the old value because the new one is not committed yet. So we guarantee that the snapshots are indeed immutable in this manner. So the client obviously wants everybody to see the new value, so it commits the transaction, and the status oracle has to perform the transactional checks. It has to check if there are conflicts. In this case, there are no conflicts, so it updates the metadata. And for example, in this example, the status oracle has a very limited memory, so it has to evict some metadata, and it has to update the low watermark that we were talking about earlier. And it basically returns to the client the committed message stating that indeed the transaction has been committed. Now, let's see what happens in case of an abort. Suppose that the client has an old transaction, a transaction that has been started a while ago, in this case at timestamp 15, and it tries to commit some value which conflicts with the concurrent transaction that we just committed. So it lost the right to HBase, and when it performs the commit to the status oracle, the status oracle will check the green box, which holds the last committed timestamp for each row, and it will see that a new transaction has already written to this row. So there's a violation of snapshot isolation, and this transaction is aborted. It is put into the abort list, and a message is returned to the client. So when the client receives the abort message, it has to do some cleanup on HBase. It has to go to HBase and remove this row which is not needed anymore because this transaction has been aborted, and it has to delete it. And this is the only overhead we impose on HBase. We actually have to clean up aborted transactions. But this is a very uncommon operation in theory, and it's not as common as locking the rows and performing all the transactional operations through HBase. So we achieve a very low overhead with this system. So you might be wondering if this centralized approach might have some problems. And obviously, a centralized server has some drawbacks. For example, it could become the bottleneck. But in our test, we demonstrated that the status oracle has very good performance, and it never became the bottleneck of the system. So in this graph, we show the maximum throughput for different transaction sizes. So the bigger the transaction, the more overhead is for the status oracle to process it. So, for example, focusing on the extreme points, for transactions that are very big with 500 rows, modified rows per transaction, because read rows doesn't count for us, we achieve a throughput of 1,000 transactions per second with 10 milliseconds latency for commit operations, which we think is very good. On the other extreme, for small transactions of two modified rows per transaction, we achieve 100,000 transactions per second with even lower latency. There's another problem with a centralized approach, which is what happens when this centralized server fails. So the status oracle uses bookkeeper to log all the operations for being able to recover the state if it crashes. There has been another talk about bookkeeper on the summit, so you might be interested in this project. And basically, after a crash, so we read the tail of the write-ahead log, and we rebuild the state. And since we are only concerned with the latest operations that have been logged to this to bookkeeper, this operation is bounded in time. So it doesn't matter how long the system has been running. Every time the recovery time is going to be the same. In this case, we demonstrated that after running the system for almost 2 hours, we crashed the system, we restarted it, and in less than half a minute, it was able to start serving the same level of requests per second again. And this is actually pretty low because usually the least timeout is bigger than this. So the recovery time shouldn't impact too much the throughput of the system, the availability of the system. Now I'm going to talk about some example use cases for this system. The main use case we have in mind while developing this system is a news recommendation system. So in this case, I'm going to explain what model-based recommendations are. Basically, you assign similar users to a cluster, and then you train a model for each cluster. And when you receive a new article, you evaluate it against all the clusters, and you recommend it to the users. So when users read articles or perform some actions, you might end up training again the models. So you have several operations at the same time on different kinds of data. You have to update the users, you have to update the clusters. Since several users belong to the same cluster, there might be concurrent accesses to the clusters. And this is a really common case where you actually need transactions if you want to be sure that you won't have problems of concurrency problems. So what are the advantages of using Omid for this use case? So we know that all operations are consistent. All the updates are consistent, and also the queries. And you might say that consistency is not actually needed for a recommendation system. I mean, it's not like we are dealing with money, for example. But if you want to be certain that you won't run on corner cases, and you want to stop serving maybe content for a user, you actually want to make sure that your system is consistent. If you have transactions, you are always guaranteed that there won't be any corner cases you have to care about. Otherwise, if you want to implement some algorithm, you need to think what happens if there are concurrent updates to the cluster. How can I update the model concurrently? Should I keep logs while updating the model? There are several corner cases that are completely solved using this kind of systems which implements transactions. So as I said, for example, there are several problems we solve using transactions, such as what happens if a cluster is being splitted several times concurrently. Maybe some clients end up without belonging to any cluster, and you stop serving them content, and you don't want that. Also, what happens if you query the system while a split is taking progress? Maybe something bad happens, and you don't want that as well. So this is an overview of this use case. Basically, you have lots of concurrent events coming into the system, new articles, and also user actions that train the models. And you have several workers working in parallel and processing each new event. each worker updates the data store, and you are guaranteed that they'll see a consistent view and they'll leave the system on a consistent state at all times. So when you have concurrent queries to the data store, you'll always have a consistent view of the models, for example. There are other possible use cases, such as the original one that Percolator addressed, which was to update indexes incrementally. So in a previous talk about HBase, somebody was asking about secondary indexes. So this is a good use case for transactions, because if you don't update your index, secondary index atomically, you might end up with an inconsistent state on your database, and then you have to handle these cases at the application level, which increases the chances that something goes wrong, or the chances of having bugs on the application. So there was some people interested on a generic graph processing system that used Omid, although that is not public yet. And there are other use cases, such as adapting existing transactional solutions to HBase. So if you have some transactional business logic that runs on, that depends on transactions, and you want to move to a NoSQL solution such as HBase, it's much easier to have the same features on the new system. So just wrapping up, I'll explain what are the current challenges we are dealing with right now, and what are our plans for the future for this system. So one of the problems is that load is not automatically distributed across the cluster. So if some machines that receive events have a higher load, this will be the bottleneck to the system. We don't distribute it automatically, although obviously you can do that at the application level. Also, we have some other problems, well, not problems, but if your application logic is too complex, this will lead to big transactions that are more likely to conflict. If they touch many rows, then they'll probably conflict more, and also are more expensive to retry. If you have a very long-running transaction that aborts, you have to retry it again and run the whole computation again. And basically, we think that this API, which we provide, is very simple, but it's also a bit low level for data processing applications. So our current effort is to build a framework for incremental processing. We think we achieved, we made it possible to have incremental processing applications with this work, but we want to make it even easier to develop new applications with a framework. This framework will provide a simpler API, will be trigger-based, so it will be easy to decompose complex operations into smaller ones, which are consistent in themselves, and also will allow you to scale more easily. It will distribute the load more evenly across your cluster. Also, we want to work on the user side of things. We want to provide debug tools, better metrics, and so on. So we want to be developer friendly. And another point we might work on is a hot failover solution. So right now, what we have in case of failure is a call failover solution, where we start a new instance, it recovers the state, and it starts serving again. And sorry, we might move to a hot failover solution, which will decrease even further the recovery time. So this is it. I'd like to say thanks to all the contributors to this project. Some of them are here, so thank you. And so please try it, and if you have any questions, use the mailing list of the project, or feel free to contribute patches, of course. So you have any questions? Sure. Sorry? So the the question is how we ensure that the timestamps are unique. The process that assigns timestamps is the status oracle, which is centralized. So when we start a transaction, the client communicates with the status oracle and it receives the timestamp from the status oracle. So if the oracle fails, we start a new oracle. It recovers the state from the bookkeeper and it knows which IDs have been already given. No, the timestamp is synthetic, so it's not the time itself. So it's a sequential incremental number.
My question is on you said that it was row level locking.
Mm-hmm.
For instance, we're working with HBase. I would expect something like column level locking.
Well, rather than locking conflict detection, we don't do any locking.
No, okay, but column level.
Yeah, I mean, right now we implemented row level conflict detection, but it's really easy to increase or decrease the granularity of the conflict detection. So it's very easy to actually check for conflicts at the column granularity. So it would be possible to extend it quite easily. Yeah. Sure. Sorry? So, well, we guarantee that transactional accesses to the database are consistent, and they guarantee snapshot isolation. So you might have so clients write directly to HBase, so the write is visible to anyone that doesn't use the transactional API. But if you use the transactional API, you guarantee each client guarantees snapshot isolation on their own, and they will ignore any uncommitted value. So that's why we guarantee that all the updates and all the reads are consistent. Yeah, but snapshot isolation guarantees that you see all the values that have been committed when you started the transaction. So you start the transaction, you start scanning, and now another client does the commit after you started the transaction. So the values that this other transaction has committed, you don't see them because they are outside of your snapshot. So afterwards, if you start a new transaction and retry the scan, you'll see these values. So, any other question?